Welcome to the Software People Stories. I'm Shiv.
I'm Chitra.
And I'm Gayatri.
We bring you interesting, untold stories of people
Associated with the creation
Or consumption of software-based solutions.
You'll hear stories of what worked,
and sometimes what didn't,
you will also hear very personal experiences.
and insights that would trigger your thoughts
And inspire you to do even greater things.
I continue my conversation with Mike Bowers, the chief architect at FairCom, in this episode. In this conversation, Mike discusses how to identify someone with an aptitude for becoming a software architect. We also talk about the qualities of a good software architect and how you can identify if you have the aptitude to become an architect. In short, he says that a software architect should be a well-rounded programmer with a strong understanding of design and practicality. They should be able to see the big picture and translate that vision into a functional system. Talks about how he interacts with the various team members and some career tips for aspiring architects. Listen on. So since you are into databases, this is one question I have to ask about handling unstructured data.
So I fell in love with databases back in the early 80s. A SQL language. A SQL was just revolutionary, and it started in the 70s, but in the 80s was where it was really starting to take on popularity. And but an SQL stands for structured query language, right? So the idea is you structure your data you create buckets to hold your data. So a table really is a bucket to hold the data. Every field in the table is a property that is a bucket to hold a very specific piece of data. The challenge with relational, though, is if you don't define a place to put the data, you can't store it. Well, that's a really big problem because you have to define a place to put every single thing you could think of storing. The second problem is you change your design over time. You always will. And that's where back in the 70s and 80s and 90s, when waterfall was the approach, and you could design something for a couple of years. That wasn't a problem because your designers would really think ahead 10 years, and you could build a database system that could stand the test of time for many decades, or at least a decade. But today, when we're agile, no one wants to take the time to spend a couple of years designing anything, and maybe a couple of weeks, maybe a month or two if you're really lucky. And so data design is not being done as much. So if you don't have a place to put the data, you can't store it. And then if you want to change your data, it breaks everything in relational. It changes your code, it changes the database. And that's expensive. That's super expensive. So in the agile world, working with relational is incredibly expensive because of all the work you have to do to refactor your database, your code, and make sure they all work again with QA. It's too expensive. So the answer is to go to a flexible data format, or a partial answer. It's still a red herring there. People don't realize. If you go to the unstructured data, which is really a differently structured data. So JSON's highly structured. So it's one of my pet peeves is people call that unstructured, which means it implies that relational is the only structured database. Well, JSON is highly structured. And if you put a JSON schema on it, you can even do more rules on the structure than SQL can do. So it's differently structured. But you get more flexibility with JSON. So then it works better with the agile world. But the red herring, or the elephant in the room that people are hoping that NoSQL will solve, is that the refactoring problem. What if I change my data structure? Will I have to change my code? Well, actually in JSON, it's even worse in many ways than relational because JSON's hierarchical. And E.F. Codd showed back in the 70s when he designed the relational model, hierarchies are brittle. If you, for example, if you have an order and you stick a customer in the order, where you put it in the order matters. And if you change where it goes in the order, you break all the code. So hierarchies are even more brittle than relational, but both are brittle is the reality. So I've been working on, I'm really excited about this. I didn't know you were going to ask this question, but makes my day because I've made a breakthrough in the last 10 years in studying how to solve this. And we're building this at FairCom. This is why I'm working at FairCom. I found a way to make a database that is future proof, that no matter how you refactor your database, it doesn't change your code. That's what Cod was trying to do. He got closer, but he failed. No one's succeeded yet, but I have actually on the verge of finishing, about a year away of implementing one more feature. And then we will have this system where you can refactor your database without breaking your code. You can refactor your code and have new things in the database simultaneously. It allows you to have old data and new data. It allows you to have old and new views of the same data at the same time. So your old versions of the app work and your new versions of the app can take advantage of the new data structures without breaking either one. And that's a whole industry game changer. So
yeah, sounds very exciting. Yeah,
I'm excited. I'm
Yeah.
totally excited
Yeah.
about it.
So I don't know if this is kind of related in some form or the other. What is your take on graph databases?
Oh, I love graph. So the evolution is went from hierarchical mainframe to flat SQL to a variety of NoSQL solutions, which are more like specialized use case databases more than not. But graph to me is the evolution beyond SQL. But graph, there's two flavors of graph. There's an RDF graph, and then there is the property graph, and they're very different. They're trying to bring them together, but they're not quite doing a good job. There's different technologies, and I've used both types very extensively. The challenge with graph is the same thing. It's even more susceptible to breaking your code if you change graph, because graph is even more flexible than JSON is. And you can refactor it very quickly, but every time you touch the graph and refactor it, you're breaking your algorithms and your data structures and everything in your code. So it's very vulnerable to that. So part of this, what we were just talking about with making a database that doesn't break your code when you change the data, I've done that for graph. So I call it object graph. So the next generation of graph is to go from RDF the next generation I call object graph. And it takes you from RDF. So if you look at the evolution, it goes from RDF to property graph. Object graph is the next evolution. And this object graph is the solution that allows you to do graph programming and graph algorithms to answer questions that SQL cannot answer and give you an interface that won't break your code when you refactor your graph, because you're going to refactor your graphs more than even your SQL or your JSON. So I love graph, but it's because it can answer questions that the others can't. But it also can't do things that SQL can do. So my ultimate goal is to have a database, which is what I'm building right now. That's a SQL database, a graph database, a JSON database, all in one, on the same data at the same time. And so we've got the JSON, we've got the SQL now. My next step is to finish the graph algorithms to do things like the nearest neighbor, the closest path, the cheapest cost. Those are questions graph can answer. And build that in on top of your to work side by side with your SQL and with your JSON and do it through an API that is unbreakable for your application.
I can see a lot of possibilities of use cases like that.
Yeah.
That too, with now this whole generative AI, I say that it is all about predicting the next possibility or the next edge that I can traverse to see the next node or build things and all that. The associated thing about Gen AI, this is not so much about this part. Whichever is the form of database that you use. Now, people say one of the big threats is through data poisoning.
Yes.
Right? Somewhat like the SQL injection that we had, or the cross-site scripting, or the supply chain attacks, and so on. This is so subtle that data can be poisoned, nobody will know, and the behavior would have changed. So in designing databases or designing structures, looking at data structures and so on, do you think, or how far away are we from building maybe resilient or self-protecting data structures?
Well, to me, it's not the data structure that's the problem. It's the data in the data structure that poisons it. And actually, poisoning is more of an active thing where some malware person, some attacker is poisoning your data, or users are having fun messing with your data and poisoning it for fun, or it's just accidentally getting poisoned because users do what they do without even thinking about it, and then the computer emulates the users, right? And so all of a sudden the computer is swearing and saying all these politically incorrect things at the users and treating and abusing users because there's abuse on the web, and then you're going like, oh gosh, IBM, why are you abusing your customers? Well, that's because the customers were abusing IBM and they just copied it. But I think the problem isn't the structures, it's the training. And this is the biggest caveat with all of machine learning and in artificial intelligence is the training set data you use. Because as I've been working with this over a decade now with data scientists, the biggest challenge is to get a curated set of data that is not poisoned, does not have bad data in it, that you can train your model on. And if you train the model on good data, then it will behave the way you want. Well, that's very expensive because you have to get the curated set of data. It has to be a large set of data. To curate it, you have to get humans who you trust to go curate it and crowdsource it or however you do it, but you have to trust what they're doing. And then you have to train on that data. So that's one factor that's gonna, you can't get away from the training of the data. The second part that I think something where you're driving to is the semantic graph. The graph database, especially the semantic one, which was designed for this use case, you could create knowledge graphs, and knowledge graphs can inform the model, but knowledge graphs are hand created. They're not even trained. You go in and knowledge graphs have been around forever. People have tried. I know you've been through this. Back in the 80s, 90s, and the 2000s, people were building knowledge graphs, hand curating them to say, this is the knowledge that's in our subject matter experts' brains. We're going to put it into a graph so that we can then codify how they think. And the medical community is actually pretty good at doing this. I met a doctor a few years ago who took his entire experience with diabetes, and he put this in treating diabetes and also all the problems with diabetes, symptoms and everything. He put it into a knowledge graph that he created with his team of doctors. And they put it into the system in their medical hospital program. When you come in, the graph diagnoses the patients. So they built an application that asks the right questions, and then the graph reads the answers and then answers it like a physician would answer. And they got very high success rates. Now, they don't just let it run without a physician being involved, but it really cuts down on the work a physician has to do because it points you in the right directions. And they're actually quite successful with that. So you combine a knowledge graph with a trained algorithm, you get the best of both worlds. And they're two different technologies. Machine learning is all statistics. It's all about probabilities and classification and drawing the line and say, okay, if I get data that looks like this, it's this thing. Like if it's apples, is it a red apple or a green apple? Is it an apple or an orange? And it can classify and bucket things. That's what machine learning does. Classifies in buckets. And then you can put layers on top of that to generate things as well from the buckets. But the semantic graph, the knowledge graph, is a classifier as well, but it's a human classification. So you add the human classification to the statistical classification, and you get the best of both worlds.
Yeah, interesting. What I had in mind, maybe it's a sci-fi idea, which is like we used to have these check digits to make sure that the rest of the digits are all okay.
Oh, yeah.
Yeah. Or probably even some of the blockchain approaches where you make sure that something cannot change without being noticed.
Oh, yeah. And machine learning is perfect for that. Completely. Because you train it on what's good, and then it'll classify anything else as not good very, very reliably.
Yeah.
It's great for fraud too, because they use that in fraud for the same exact thing.
Fraud, yes. Yeah. So going back to where we started when you talked about your interest in music.
Oh yeah.
right? And I see that the way children learn music, right? It's not just the mechanical movement of their fingers or the mouth and stuff like that, but it's also something that they need to imbibe these patterns, something that they know, whether it is a symphony or a cacophony. Similarly, when you mentioned that different strokes for different folks, and then how you explain the level of detail that you go to explain your thoughts to the developers, is there something that we can learn from the way music is taught or music is learned to learning how to code, how to write good code? Now, for instance, even if I am not trained in music, when I listen, I can say that no, this is off key, right? Probably something is not right. So if I can do the same thing, like you call the code smells, are there code sounds that we can think of?
Yeah, absolutely. So when you're training a musician, or a young person to do music, you're you really there's some basic things about moving your fingers to play the notes or to hold the clarinet or flute in the right way. There's some technical things you have to train them. But when you get past that lower level of push the note this way, or then you can teach them the patterns of the music itself. And one of the first things you teach a student is rhythm. And so the rhythm is very mathematical, right? It's really base two, by the way, base two or base three. So all music is base two or base three math. So that's really fun. We don't talk about it that way when we train music, but you have 2/4, you have 3/4. And so we just talk about fractions that are based on twos and fractions based on threes. And you learn how to group twos and threes together to create higher levels of rhythmic patterns. So you're teaching patterns, and as the student learns the various patterns and how you notate the pattern, they can then they connect different parts of their brain. So there's the interesting thing about the human brain is it's not one brain, it's many brains in one. So I mean, I guess there's one organ, but there's many parts of the brain that are specialized. So there's a hearing and audible part, there's a language processing part, there's a musical rhythmic part, there's a musical pitch part, there's all these different parts. And so your mind has to use all of those. And then when you're playing an instrument, you're touching and playing, your hands are moving very quickly to play the notes. There's a physical part of your brain that controls your hands and your mouth. If you're using a wind instrument or a violin, all those things come together. So when you're playing music, your whole brain lights up. And music will make a person smarter because it exercises the whole brain. It's the best exercise for the whole brain. And that's scientific. That's really fun and proven. So when you're teaching, you teach patterns in order to take simple things and group them to more complex things. Then you learn the next level of pattern. Then you break, and then you learn another level beyond that. So it's all about patterns upon patterns upon patterns, or levels of patterns, right? So then you learn pitches, and you learn patterns of pitches. Then they call that harmony when you group pitches together, and you can play chords. There's another thing called counterpoint, where you have two melodies that play against each other. There's ways to make that work. There's rules on that and patterns for that. So there's patterns for chords, patterns for counterpoint, patterns for rhythm, patterns for the different instrument sounds. They call that timbre. And so the human mind, as your student, is learning, sort of like machine learning, really. You're learning how all these patterns are working, and it takes time for your brain to absorb the pattern. And what's really fun is it absorbs it just like a machine learning algorithm. Humans cannot look at a machine learning algorithm and know how it works. You don't know how because the statistics are so complicated and we don't think that way. Well, there's lots of parts of our brain that work that way, like speech. Do you really know how you think when you speak, or you just think? We learned that. And so it's the same with music. You learn these patterns intuitively. And so I can sit down and hear a piece of music and intuitively know what it is without thinking. But when you go to music training, then you start to say, okay, this pattern looks like this on paper.
Mhm.
When you're in the music notation. So now that's like code. music is code. When you're reading music on paper, it is code. We've codified the oral experience into code on the page. That's why musicians are often good coders, because that's all we're trained to do is read code on the page and play it, or hear it and write it into code. Or if you're a composer, write the code, which is what a developer does.
So how can that help us get people to learn coding faster or to do better coding?
Yeah. So it's about the patterns and levels of patterns. So in the beginning, when you teach a coder, you teach them some basics like, here's a statement, here's a function, and you teach them the pattern of a function. Here's an array, here's a data pattern, and what you can, and then you teach them what you can do with it. Musicians don't just learn a pattern, they go and play it, right? So when you teach a programmer, if you're a programmer educator, you teach them a data structure like an array of strings. And you say, what can you do with this? Let's go write a program that does different things with an array of strings. Then you teach them an array of objects. Now, what can you do with an array of objects? And they go write a program to do it. Just like a musician would say, now you learned the harmonies, you learned a 1-4-5-1 chord progression. Now go play it, and I'll go improvise on it and go use it. It's the same thing in programming. You said, now here's a hash map. And now how would you use this to do things? And I will go write a program and use it. And you teach them to think in terms of patterns and using the patterns and practical application of them. If you apply it practically, then the people will learn it and understand the why behind it, and they'll have a lot more fun than just saying, I bet you've been in courses. I was in courses that just drive you crazy. You just want to poke your eyes out. Here's the function. You can pass parameters into it. And you're like, gosh, there's no value here at all. Where's the pattern? Where's the practical application? And then, in fact, I had a nephew I just talked to yesterday. He was taking a programming class, because I tell all my relatives to take programming classes. Mm-hmm. And he was taking this. He goes, I hated this class. Functions were okay. It was Python. I learned functions in Python, but then they taught me error handling, and I didn't understand it, and there's no practical use for it. This is stupid. And I'm going, oh, what a terrible teacher. He didn't teach the pattern and how you can use it and why it would benefit you and what you can do with it. So musicians are all practical. We have to play. Because we have to play what we code or what other code, so if you're a musician, you're going to do that. As a programmer, you're going to practice what you learn. You learn a new pattern, you're going to go out and write tons of code using it. You can't stop yourself. You're so excited, like, oh, I can't wait to try this hash map in this scenario, and see what it will do.
Good. I think, we've been going for a long time, and we have a few more minutes. As I mentioned, I would like to ask some career tips, but then after our conversation, I'm going to ask that slightly differently. One is, how do I find out if I have an aptitude to be an architect, or should I be a born architect?
Then that's yeah. So the aptitude for an architect is, number one, is abstract thinking. You have to be able to think abstractly. You also need to be practical. There are too many architects that are ivory tower architects that were book learned, and they're the worst nightmare for a developer, because they'll say it should work, but they've never done it themselves. So a good architect also needs to have done it. Like, I programmed in dozens of languages. I programmed every algorithm. I've written compilers. I know how to code at the deepest levels, at the highest levels. I know the patterns. So a good architect needs to be a fantastic developer, needs to understand data structures, needs to understand how to use them. And then when you're making your designs, you're going, okay, you're using this database technology. I know its limitations. And I know if you do it this way, it'll work really well. If you do it the other way, it won't work well. And then you design it to work with the technologies. You have to be very practical, or the developers will just ignore you. And so, in fact, yesterday I was having a conversation with a Java developer, and he became a manager, and he had an architect that was ivory tower, and it was a nightmare for his whole team. They had to get rid of him because he just made designs that were impossible to build, because he didn't care about, it was just all ivory tower book learned perfection, and it wasn't practical. So I guess a good architect's like a good performer in music. You can read the music, you've done the music, and you can play the music, And then, an architect's more like a conductor now. You can conduct others in performing because you've been there and done that, and you know how it works.
So the second question is, assuming that I probably have a little bit of an architect in me, at what stage of my career should I consider? Should I start, when I start my career, can I become just an architect by doing whatever? Or do I need to get some experience and then look at becoming an architect?
Well, you need experience to be an architect because otherwise you'll be turned into one of those ivory tower architects if you get the job, and your developers will hate you and you won't be successful. So you need, I recommend, I was a programmer for a good 20 years before I became an architect. But I knew I was going to be an architect all along because my mind works that way. So here's one tip for you if you think like an architect. An architect always wants to know how things work, and they want to see the pattern of how it works. So everything in my life, it's not just programming, everything like music, but also everything I'm doing. If I, I could just go on. To keep it short, I'll just say everything I do, I'm analyzing. I'm analyzing everything I do. What is the pattern behind it? How does it work? How can I do it better? How could I design this and use this to build this? If you're constantly thinking like that, you're wired to be an architect. If you're constantly, the opposite though would be a good developer would just say, give me a Jira ticket, tell me exactly what to build, I'll code it. If you love that, you're not an architect. Architects go insane at getting a small little assignments and just coding them. And we need both. There's not like one is better than the other. They're just different. And so, don't feel bad if you're not an architect. That's not the end all be all of all things. Architects are like the composers in the music world. Architects write the music, but if you didn't have anybody to play the music, well, then we wouldn't hear it. So that's why we have orchestras and musicians and pianists and violinists, right? So we need all the musicians and we need the composers. Architects are the composers. So you have to be thinking like a composer and really be obsessed with patterns and how to use them in the real world. And if you're that way, learn how to write the music, learn how to write your code, be an excellent composer, be an excellent programmer, and then you can become a great architect if you have the right mindset.
Oh, that's wonderful. I think I got a new perspective, or maybe multiple perspectives, on how an architect thinks, the mind of an architect. Yeah. Thanks a lot, Mike. So thanks a lot once again for coming on the show and sharing your story.
My pleasure. So nice to meet you and have this wonderful conversation.
We thank Siddharth for the music and Anita for promoting the Software People Stories.
If you like this episode,
Please subscribe on your favorite podcast client.
And spread the word in your network.
if you'd like to share your story,
Contact us at podcasts@pm-powerconsulting.com.